And welcome. I am so excited you're here. We are diving into something today that is absolutely foundational to the future of technology. You know, we hear about artificial intelligence, Industry 4.0, and these massive futuristic smart factories constantly, right? A single modern factory can crank out petabytes of data in just a week. But here is the hidden reality. None of that fancy, high-level software works if the actual physical machines on the factory floor don't speak the exact same language. In this explainer, we're going to decode how these machines actually talk to each other, and we'll break it down step by step to keep everything crystal clear.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the language of machines, move on to PLCs and smart machinery, step up from Modbus to OPC UA, explore the SEX/GEM standard, and finally, look at building true smart factories.
All right, Section 1, the language of machines. So I want to pose this question directly to you. How do factory machines actually talk to each other? We toss around buzzwords like big data and system integration all the time, but before we can pull a single drop of data into some shiny dashboard, we need a physical and logical way to pass information back and forth between chunks of metal and silicon. Without a shared language, you just have isolated islands of machinery. To really grasp this, let's look at how factories have evolved over time. Back in stage 1, it was all about traditional, mechanical control. Very simple. Then, stage 2 brought in basic automation using PLCs. Stage 3 was a huge jump, introducing industrial PCs to create actual smart machinery. And finally, we arrive at stage 4, full Industry 4.0 networked integration. This is where data just flows seamlessly across the entire factory ecosystem. It's an incredible progression from simple physical circuits to highly intelligent networks.
Moving into Section 2, PLCs and smart machinery.
Let's define the absolute workhorse here, the PLC, or Programmable Logic Controller. Think of the PLC as a really obedient worker. It just sits there, takes in signals from sensors, and executes fixed control logic, usually written out visually like a ladder diagram. It reliably turns motors on, opens valves. It's incredibly stable, but its functionality is completely fixed. It only does exactly the pre-written routines you give it, no more, no less. But what happens when your production needs to be customized? Well, that's where IPCs, or industrial PCs, step in. Adding an IPC is literally like giving that obedient worker a super-powered brain. All of a sudden, your regular equipment becomes true smart machinery. With an IPC, the machine can process data right there on the edge, what we call edge computing. It handles remote monitoring, and it can even swap out complex production recipes on the fly. This is absolutely critical for modern manufacturing, which demands high-mix, low-volume customized runs.
Section 3, from Modbus to OPC UA. Now what's really interesting here is the massive difference between the old standard and the new one. Think of the old way, Modbus, like an old, dusty warehouse. You want data? It points you to an arbitrary numeric address like 4002, and there you find the number 930. But what on earth is 930? Is it temperature, pressure, pounds? You have absolutely no idea unless you dig up a separate external manual. Now contrast that with OPC UA. OPC UA is like a highly organized smart library. You don't need random addresses. You just search for an object name, like reaction tank 3 upper pressure, and boom, the system hands you the value, the exact unit of measurement, and all the context you need.
The data actually describes itself. And this is exactly why OPC UA is the engine driving Industry 4.0. Because the data carries its own labels, it's totally decoupled from those underlying hard-coded PLC addresses. Think about it. If an engineer updates the software and a physical address changes, your whole system doesn't crash anymore because you're still just asking for the object by its name. It upgrades factory communication from simply passing cold numbers around to exchanging meaningful, rich information. This is what lets your IT systems and your operational technology integrate seamlessly. It's true real-time machine-to-machine dialogue.
All right, Section 4, the SECS/GEM standard.
Now, if you're in an industry that needs extreme precision, SEX/GEM takes things a massive step further. It isn't just about defining what data looks like. Think of SEX/GEM like a meticulous movie script. It strictly dictates exactly how the host system and the manufacturing equipment interact at every single conceivable moment. It controls machine behaviors, how sudden events are reported, and exactly how alarms are triggered and managed.
And this table brilliantly illustrates just how rigorous that script really is. If you're integrating semiconductor equipment, you absolutely have to know these IDs. SVIDs let you read the machine's current status. CEIDs represent sudden, active events the equipment reports to you. ALIDs are specific alarm codes for when things break down or malfunction. And RCMDs are the remote commands sent from the hosts to control the equipment. Honestly, knowing these IDs is like having the ultimate cheat code for integrating advanced manufacturing equipment into a central system.
Section 5. Building True Smart Factories. Let's bring this explainer back to the practical reality of factory management.
I absolutely love this idiom from our source material. A good cook cannot cook without rice. It's so true, right? The crucial point here is that you cannot make something out of nothing. It doesn't matter how incredible your IT dashboard or your software automation is, it cannot magically create data if the physical machine on the floor doesn't have the proper communication modules built into it. If the equipment can't send the signal, you can't collect it. It's really that simple.
And honestly, this causes a massive headache in traditional factories. Process engineers often buy equipment based purely on the manufacturing budget and mechanical specs, completely ignoring data communication. Then, when the factory tries to upgrade to Industry 4.0 later on, they realize that retrofitting those old machines with new communication modules is prohibitively expensive. We're talking astronomical costs. So to solve this, you need these 3 steps. Step 1, define your future communication specs up front. Step 2, and this is a real game changer, mandate that the IT department signs off on all new equipment purchases. IT has to guarantee the machine speaks the right language. And step 3, require the vendors to fully install and configure those communication modules before the machine is ever even delivered.
To wrap things up, let's zoom out for a second and look at the bigger picture. If setting clear, intelligent communication standards is revolutionizing factories today, just imagine the impact on our broader world. How will these exact same principles reshape the interconnected smart cities of tomorrow, or complex power grids, or the Internet of Vehicles and massive healthcare systems? Everything in our future relies on complex equipment talking to each other efficiently and intelligently. Decoding the language of machines isn't just about manufacturing, it is about understanding the very infrastructure of our future. Thank you so much for hanging out and diving into this explainer with me today. Stay curious and keep learning.